In this video, I will discuss the key data pre-processing and modeling steps used in the ABC Bank Notebook, explain why the selected machine learning models are suitable for business problems, and reflect on the insight gained from the result, particularly regarding data preparation and feature engineering. The business problem addressed in the ABC Bank Notebook is a binary classification task, predicting whether a customer's credit card application should be approved or rejected. This is a typical financial decision-making problem where both prediction accuracy and reliability are important because approval decisions have real financial and regulatory consequences. The machine learning workflow in the notebook begins with the data exploration and processing. The dataset contains a mix of numerical and categorical variables, missing values, skewed feature distributions, and class imbalance. These characteristics are very common in real-world financial data and must be addressed before training any machine learning models. Key preprocessing steps include handling missing values, encoding categorical variables, transforming skewed numerical features, and separating predictors from the target variable. The notebook compares different approaches to categorical encoding, specifically label encoding and one-hot encoding. Label encoding is simple to implement but may introduce artificial ordering among categories, while one-hot encoding avoids this issue by representing categories as binary variables, at the cost of increasing dimensionality. For numerical features, transformations are applied to reduce skewness. These steps help stabilize the model training and allows models to learn patterns more effectively. Without addressing skewness, certain features may dominate the learning process and negatively impact performance. The notebook also applies principal components analysis, or PCA. PCA is used as a dimensionality reduction technique that transforms the original features into a smaller set of uncorrelated components while retaining most of the variance in the data. This can improve computational efficiency and reduce overfitting, although it comes at the cost of reduced interpretability. After data processing and feature engineering, several classification models are trained and evaluated. Logistic regression is used as a baseline model. It is well suited for this business problem because it is interpretable, efficient, and widely used in credit risk analysis. In a banking context, interpretability is especially important, as decisions often need to be explained to regulators and stakeholders. Random forest models are also used in the notebook. Random forests are capable of capturing nonlinear relationships and interactions between features, which are common in customer financial behavior. Compared to logistic regression, random forests often achieve higher predictive performance and are more robust to noise and outliers, but they are less interpretable. In addition to manually selected models, the notebook uses H2O AutoML. AutoML automatically trains and evaluates multiple models, including ensemble methods, and selects the best performing model based on predefined metrics. This approach is used for benchmarking and performance optimization, but it still relies heavily on well-prepared input data. One of the most important insights from the results is that data preparation and feature engineering have a significant impact on model performance. Choices such as encoding methods, feature transformations, and the use of PCA directly influence accuracy, stability, and generalization. In many cases, these preprocessing decisions have a greater effect on performance than the choice of algorithm itself. The strengths of the data preparation techniques used include simplicity, efficiency, and improved model performance. For example, one-hot encoding avoids category ordering bias. PCA reduces dimensionality and computational costs, and feature transformations help models learn more effectively from skilled data. However, these techniques also have limitations. Mean-based imputation can reduce variance. One-hot encoding increases the number of features, and PCA reduces the interpretability of individual variables. These are several ways the result could be further improved. More advanced imputation techniques could be applied. Feature selection method could be used instead of four-dimensionality reduction, and hyperparameters turning to the further optimized model performance. Cost-sensitive learning could also be considered to better reflect the real-world costs of incorrect approval decisions. In terms of real-world implications, the outcomes suggest that careful data preparation is essential for reliable and responsible machine learning. In financial applications, approval decisions are highly sensitive to pro- to pre-processing choices, and model interpretability remains critical for ethical and regulatory reasons. Overall, the ABC Bank Notebook demonstrates that successful machine learning systems depend on a well-designed end-to-end workflow. Data preparation and feature engineering are not just preliminary steps, but core drivers of model performance and real-world impact.